Hi everyone. In this video, I will explain the working of the vector voltmeter. The vector voltmeter is used to measure the voltage and the phase difference. This measures the voltage of two signals simultaneously. It can also measure the phase difference between them. This is the block diagram of the vector voltmeter. The block diagram can be divided into 5 parts to easily understand the working. As you can see, there is a voltmeter section over here which measures the voltage. It can be connected to the first input or the second input, and so we get the voltage reading. We have a phase meter here which measures the phase between the two applied input signals. This block diagram can be divided into 5 parts. Let's look at the first part. The block diagram consists of two RF to IF converters. Here you give your RF signal, then you have a sampling gate and a 20 kHz tuned amplifier. This comes under the RF to IF converters. The given RF signal is converted to an intermediate frequency signal of frequency 20 kHz by sampling it. Sampling is done by giving sampling pulses. That is shown here. This generates the sampling times, and so using a capacitor which is part of the sampling circuit, we are able to sample the high frequency RF signal, that is in the range of 1 MHz to 1 GHz, and convert it to a low frequency intermediate signal of 20 kHz frequency. This allows us to use the signal at a lower frequency and measure the voltage or phase. So the first two blocks are the RF to IF converters. Next, we have the automatic phase control section. The automatic phase control section ensures that the phase of the IF signal, which we convert from the RF signal, is maintained in same phase as that of the RF signal. So there is no phase difference between the RF signal and the IF signal for both the input signals, that is input A and input B. This unit ensures that the phase is maintained the same. Here we have a 20 kHz reference oscillator and an automatic phase control section, and then a voltage control oscillator and a sampling pulse generator. As we have previously observed, this provides the sampling instance for the RF to IF converters. After the sampler, the signal that is sampled is given to the automatic phase control section. This section ensures that the phase is maintained same for both of these signals. The 20 kHz reference oscillator serves as a reference signal here. The automatic phase control section provides through the voltage control oscillator a control voltage which adjusts the sampling pulse generator to generate sampling signals such that the phase is maintained same. This is our third section. The fourth section is the voltmeter section. The IF signals now, after passing to the tuned amplifier, are given to an attenuator and an amplifier, which are part of the voltmeter section. You can connect this switch to any one, either to section A or section B, so that you get your DC voltmeter through the DC voltmeter, you get your voltage reading. The amplifier, along with the attenuator, consists of filters and rectifiers in order to convert the signal to a DC signal so that the voltmeter reads the voltage. This is our fourth section. Finally, there is a phase meter section. This section measures the phase difference between the two signals. The IF signals here are sent to an amplifier and limiter. This block provides an output as a square signal. When you amplify a sine signal and then you limit it, you get a square signal. Then we observe that we are giving a plus 60 degree phase shift here and a minus 120 phase shift here. We will come back to this point why we give this phase shift. Next, we have trigger amplifiers, whose purpose is to provide spikes, that is like impulses, which serve as triggers for the bistable multivibrator over here. This input is connected to the set terminal of the bistable multivibrator, and this is set to the reset terminal of the bistable multivibrator. Depending on the inputs, we get an output. That will be a square wave. The bistable multivibrator, as you know, has two stable states. So it will be either high or low, depending on the inputs. Here we have a current switch, which is nothing but our transistor, which is connected to a constant current source, and that is connected to the phase meter. Let us understand clearly how this section works. The RF input signal, or in other words converted to IF, so let's consider this as the IF input signal A, that is the first signal, is plus 60 degrees phase shifted. So this is the plus 60 degree phase shift. The second signal is minus 120 degree phase shifted. If you observe, these two signals are then 180 degree out of phase, which is shown here. These are shown as inputs to the bistable multivibrator. This is to the set, this is to the reset. First signal, second signal. So based on this, we get a symmetrical wave. That means when the first signal is in the negative half, and at that point you have the second signal in its positive half. So they are 180 degree phase shifted. What we can observe is when two input signals are in 0 degrees phase shift, that is when there is no phase shift in them, when it comes to the bistable multivibrator input point, you find that these two signals are 180 degree phase shifted. And so the bistable multivibrator provides a symmetrical wave as an output. This symmetrical wave then is connected to the current switch here, which goes on and off, turns on and off depending on the symmetrical signal given here. So when it is on, it connects the constant current source to the phase meter. When it is off, it does not connect. And so the phase meter is designed such that when there is a symmetrical wave, it reads a 0 degree phase shift. Now, if the input signals have a 180 degree phase shift, if there is a 180 degree phase shift in them, then here 180 degree or plus 180 degree or minus 180 degree or any other angle, then the inputs at the bistable multivibrator no longer are 180 degree out of phase, but some other angle, which produces an asymmetrical wave instead of a symmetrical wave. Now, when we have an asymmetrical wave, the current switch goes on and off for unequal times. That is, T on is not equal to T off. Then the phase meter is so designed to read the corresponding phase difference value. Now, if we go back and see our diagram, it becomes quite simple. So here you see you have your RF to IF converters, that is the sampling gate and the 20 kHz tune amplifier here as well. So with this you're converting your RF to IF. This is your automatic phase control section. This is your voltmeter section. The remaining all serves as the phase meter section. Thus, the vector voltmeter measures the voltage and the phase difference. Thank you for watching.